Hey there everyone, hope everyone's doing good. Now we're going to talk about selection sort in Python here. Fun little sorting algorithm, pretty easy to understand, pretty easy to implement. Not super efficient, but still fun. Alright, here is the source code for it. I know everyone kind of just wants to jump in, get the meat and potatoes, and jump out as soon as possible. So here it is. You can go to this link up here. It's also going to be in the description of the video, so you can just go to the GitHub here. Here's all the code for the selection sort. You can go to raw. You can copy and paste this all into your favorite text editor or IDE and play around with it yourself, so you don't have to hear me drone on for the next 15-20 minutes, however long this video turns out to be. Otherwise, we'll go ahead and get started here. So this slideshow, it's going to be in the description of the video. Here's where the code is. Wikipedia, I quote some of their definitions. Big O cheat sheet, absolutely love them. And this is where I bring up the time complexity. And then we're going to use Visual Go and TopTal Visualizer in order to kind of see how A, the sorting algorithm works in Visual Go, and then B, in TopTal, how it compares against other sorting algorithms. Alright, so this is what selection sort is. In computer science, selection sort is an in-place comparison sorting algorithm. It has an O to the n squared time complexity, which makes it inefficient on large lists and generally performs worse than the similar insertion sort. So n squared, right? That just means if I have an array of size 10, then 10 squared is 100. It's going to take 100 computations to sort that. Okay, obviously, that's really not that bad for a list of 10, but how about 1,000? How about 10,000? You can see that that it's not a very efficient algorithm. N squared is not a good time complexity. Selection sort is noted for its simplicity. It is very simple. It does have performance advantages over more complicated algorithms in certain situations, particularly where auxiliary memory is limited. All this is saying is if you're memory limited, you don't have much memory to play around with. Selection sort is pretty easy because, you just got to basically swap one or two indexes at a time. You don't need to store much in memory as opposed to some of the other sorting algorithms, which are fast but rely on more memory. It proceeds by finding the smallest or largest, blah, blah, but the smallest element in the unsorted sublist, exchanging it with the leftmost unsorted element, and moving the sublist boundaries one element to the right. That's kind of confusing. So we'll look at it here in a second. This is the sorting algorithm time complexity from bigocheatsheet.com. Absolutely love them again. Definitely highly recommend them. Go there, buy their little poster, hang it up on your wall. I did, and I look at it all the time. Best case is n squared. Average case is n squared. Worst case is n squared. And our space-time complexity is 1. So as you can see, n squared across the board, it's all red. Red normally means bad. So this is not the best sorting algorithm to implement. However, it's easy. And it's fun, and it's a good learning experience, and you may, get in a situation where you're only sorting a few elements at a time, so you could care less about, n squared. All right, here is the pseudocode. So, outer loop, we're going to start at 0. We're going to iterate over the entire array. So you'll notice a lot of times in these sorting algorithms, you have an outer and an inner loop, okay? So our outer loop starts at 0, goes to the end of the array. We're going to set our first index to be the minimum index. This minimum index thing is kind of the key thing about selection sort. We need to always keep track of which index holds the minimum value. If it's the first time through our array, and we've only looked at one element so far, then that element is, by definition, the minimum one we've looked at. So we always set that first index that we looked at to be the minimum index. Okay? Then the inner loop, which I'm going to call J, normal conventions, starts at I plus 1. Okay? It's not starting at I. I've already looked at I. I is already my minimum index, so my inner loop does not need to start at I. It can start at the next the next item over, which is J. Or I should say I plus 1. We still iterate over the entire array, right? So this differs from bubble sort. Bubble sort, remember, went to the end of the array -1. We're not doing that. Inner loops going all the way to the end of the array. For each index j, we're going to check if it's less than the minimum index. If so, set the minimum index to j. All this line right here is telling you is if we see something lower than what we've seen before, than what we're keeping track of at the minimum index, then we're just going to set our minimum index there, because the whole point of this is we iterate over the array, find the minimum value, and then basically shove that minimum value to the beginning. And that's what this is right here. We're going to swap the minimum index with the I index at the end. All right, and then we're going to go up to the outer loop and continue this whole process until we get to the end of the array, and then we're going to return the list. So plain English, for each time through the array, find the lowest value in the entire array, place it at the beginning of where we started, then start at the next element, I should say. I think I was thinking about sorting cards, right? Because selection sort is very similar to how most people will sort their playing cards in their hands if you're playing some type of card game, and continue that process. So let's see what it looks like. All right, so this is my starting condition. Here's my code in the bottom right. I basically got 3 kind of variables I got to keep track of. I got my outer loop variable, I got my inner loop variable, j, and I have my minimum index, I. And I kind of also kept track of all these down here at the bottom. All right, so let's see. When we first start, we're going to say for I in range of the list, right? So I is going to start at 0. It's going to go all the way to the end of the list. So it's going to traverse this whole thing and until it exits. Then I'm going to say, hey, minimum index is equal to I. Well, why is minimum index equal to I? Because this is the only element I've seen so far, basically. So by default, it's going to be the first or the lowest, the minimum one we've seen. So your minimum index is always going to equal to I when you first start your outer loop. Then we're going to say, hey, j, our inner loop, is going to start at I plus 1. Why I plus 1? Because I've already looked at 17 here, or this index 0. I already know that's my minimum index, so I don't need to look at this again. I just need to look at the next one over. So that's why j is always going to start basically 1 offset from I. And for each one of these, I'm going to go through and I'm going to say, hey, is whatever bucket, right, whatever element in this array or this list I'm looking at, in this case it's 12, is this less than what I find at the minimum index, which in this case is 17? If it is, then I'm going to go ahead and set my minimum index here. It's going to come over here. And then finally at the end, once j gets all the way over here and is exited, then we're going to swap, because this minimum value is going to point to the lowest value in the list, and then we're going to swap that and replace it with I. So let's look at this. Okay, we incremented minimum index to 1 because we said the value found at j, which was 12 here, right? This value here is less than the value we had previously for minimum index, so we set minimum index pointing to this. Then we're going to increment j. So value found at j, 37 here, is greater than the value found at I, so we don't need to do anything. Or I should say greater than the value found at the minimum index, so we don't need to do anything. We increment j. Now it's pointing at 19, all right? That value is greater than what we have at 12, so we don't do anything. We increment j. Now j is basically at the end of the list, right? We found 20. It's not greater than the minimum index. So j, we're breaking out of that inner loop here. And now that we're at the end, we broke out of the inner loop, we're going to do this right here. If the minimum index, which is 1, is not equal to I, right? 1 is not equal to 0, then we are going to swap them. And we do our normal kind of swapping procedures. And we swap the 12 and the 17. So 12 is going to go here and 17 is going to go there. And now that we're out of the inner loop, now we iterate the next iteration of the outer loop. So we increment I becomes 1. Again, we set our minimum index equal to I. So minimum index and I are going to equal at this very first line here. We're going to start our inner loop. J is going to start at I plus 1. So I is 1. You add 1 to that, you get 2. That's why J starts at 2 right there. And then we're going to repeat this whole process. We're going to keep checking and incrementing J, seeing if we find a lower value. And if we find a lower value by the time we get to the end of it, we're going to swap it to the start. So increment J, 19 is not less than 17. Increment J, 20 is not less than 17. So we really don't do anything because of this right here. Let me back up a slide. Okay, we really would have found our minimum index is 1. Our I is 1. So we don't need to swap because our minimum index is not equal to I. Or in this case, it is equal to I, so we don't perform the swap. We only swap if the minimum index is not equal to I. Okay, so now we iterate again over the outer loop. I becomes 2. J becomes I plus 1, which is 3. Our minimum index becomes equal to I. And we're checking, is 19 less than 37? It is. We set our minimum index to 19. We increment J. J's at the end of the list now. Well, technically we'd first check, is 20 less than 19? No. So we don't need to reset it. But J's at the end of the list, so we swap the I in the minimum index. And then we continue. I becomes 3. J becomes I plus 1, which is 4. Our minimum index is set to 37 to start with. However, now that we've seen that 20 is less than 37, we set our minimum index. This should be 4, I believe. In this, that should say 4, minimum index 4. There we go. I went back and I fixed it on the master copy. I don't think it'll be updated here yet until I get out of presentation mode. Either way, the minimum index becomes 4, and then we're going to swap those. We're going to swap I in the minimum index. Boom. And finally, I has reached the end of the array, right? We increment I's reached the end of the array. The outer loop is finished. We're done sorting. So finally, we just return the list. So this is a whole process. Let's take a look at how it looks in not just Visual Go, but let's look at Visual. Let's look at TopTel first. So again, this is selection sort here. On the top axis, we have all our different kind of popular sorting algorithms. On the left axis, we have all of our, we have a few different starting conditions for our lists or arrays. A completely random one, a nearly sorted one, a reversed one, or a few unique. So here's how selection sort works on a completely random list. All right, you start at the beginning, you go all the way to the end, finding the minimum value and throw it at the beginning. On a nearly sorted list, this is what it looks like. And then let's see how selection sort stacks up against all these other sorting algorithms. So I'm going to play them all. And it is the last one to run, last one to finish. So just keep that in mind. Okay. Now let's go ahead and take a look at it in Visual Go. This is the Wikipedia implementation of it, if you want to look at that. However, this is Visual Go. This is the same array that I started with in the presentation, 17, 12, 37, 19, 20. So let's go ahead and sort that and just watch what it does. Let's slow this down. Let me restart this at a slower speed. Okay. Boom. Swap those. This is bubble sort. 1 second. And let me get to the right one. Okay, there we go. So now I'm in selection sort. I have the same array that I started with. So let's go ahead and sort this nice and slow. Just let Visual Go do its thing. Okay, we start at 17, we find our minimum index, which now is 12. Keep going, get to the end. We're going to swap 12 and 17. Now we know that the minimum, now we know that 12, this leftmost item, is already sorted, right? It was the minimum value in the whole array. So we don't start there anymore. We start at the next one, which is 17. We're going to go through here and we're going to find the minimum value, which in this case happens to be the 17 that we already have. So we don't swap anything. That's already sorted, right? 17 is now considered sorted. So let's go ahead and keep going. 37, start at 37, compare with 19. 19 becomes minimum index, go to 20. Okay, swap 37 and 19. And we're done. List is sorted. So now let's speed this up and let's try it on another one. Let's just do a completely random. Let me see here, completely random list, and let's sort this. We're going to iterate through. We're going to find our minimum value, which in this case is 4. Here's 1. So 1's definitely going to be the minimum value, but we're still searching, right? Because we don't know that. Boom. Throw it over the beginning, start at the next one, and we keep iterating through. Found 3. 3 becomes our minimum. We swap it. Start at the next unsorted item. 4 is our minimum right now. Still got to search through the entire array to make sure that's the minimum. Eight becomes our minimum. Still have to search through the entire array. And let's speed this up a bit. So the red here is obviously the minimum pointer. The green being J. And that's it. So that's how that algorithm works. So I'm going to jump into PyCharm here. I'll start coding it up. If you're good with this and just want to grab the code right from GitHub, feel free to do it. But if you want to watch me code for whatever reason, you're more than welcome to stick around for the rest of the video. If you're going to bounce out now, that's cool. Like, subscribe. You know, if you liked it, send me a comment. If you didn't like it, send me a comment. Tell me how to make it better. So on and so forth. But, all right, let me bring up PyCharm here. And I'm going to throw, I already have a swap algorithm that I'm just going to pop in here. If you watch the bubble sort video, you've already seen me do this. All right, all I do is take a list, 2 indexes, a left and a right one, create a temporary placeholder to store one of the values. It doesn't matter which one. In this case, I'm storing the right index. I could store the left index. Literally doesn't matter. But I do have to have some type of temp placeholder. And then I just swap those two. So that's the swap algorithm. Now let's talk about the selection sort. Create a new function. It's going to take one parameter, basically an unsorted list. I'm not going to do a docstring here. All right, normally I would, but it fills all this stuff out. That's a lot of empty space that I'm not going to worry about just for this quick little tutorial video. But I do have docstrings in the GitHub repo for it. All right, remember we're going to start with our outer loop. So let's do our outer loop. It's going to start at the beginning. So for I in range. And we're going to go, range is what? Well, it's going to go from the start to the end. So length of the list. In here, remember, I need to set my minimum index variable. Min index tracker. So I'm just going to call it minimum index just to make it super clear what it is. And it's always going to equal to I at the start of this algorithm. Every time I iterate over this every time I iterate over this the outer loop, I need to set that minimum index back to I. Then I need to do my inner loop. So let's do our inner loop, which is going to be j by convention for I in range. Now remember, my minimum index is already set to I, so j doesn't need to even bother looking at I. So I don't set my minimum, I don't say for j in range I to the length of the list. I say I plus 1. Basically, start at the next element. And what I'm going to do, I'm going to say, I'm going to check if value at j is greater than, or excuse me, less than value at minimum index. Minimum index, can't type today. And if it is, so here's my if, so if the list j is less than the list minimum index, then what I'm going to do, well, I know I found a minimum or a lower value, so I'm just going to basically take this minimum index here and I'm going to set that equal to what j is. That's it. That's basically the whole algorithm. I do have to swap, so at the end here I'm just going to say, hey, so if I don't need to do a comment here for that. It's going to be blatantly obvious what it is. So if minimum index is not equal to I, then I'm going to swap and I'm going to say pass in the list what indexes I want to swap are I and the minimum index. And that's it. That's why I say selection sort is pretty simple. Pretty simple to do. Let's do some test cases, see if I actually did it correctly. Oh, I actually need to return the list, don't I? So at the end of this outer loop over here at the same indentation level, let's return the list. All right, now let's do some test cases. I got a copy that a few that I'm just gonna copy and paste in here. This is the same one that we just did in the presentation video here, the unsorted list. 17, 12, 37, 19, 20. So let's see what this comes out to be. I think I'm working in temp.py, yeah. Let's see what this is. Okay, so 12, 17, 37, 19, 20 is my original list, and sorted becomes 12, 17, 19, 20, 37. I would say that is a passing test case. Test case 2, I'll copy and paste this in. This is basically going to be roughly the same, except now I want to make sure this works with negative integers as well. So let's try that. And I would say negative 100, negative 5, 10, 2500 something, and 3200 something. I would say this side is sorted as well. So it looks like it works with negative numbers. Let's try it with a list of 0 elements. Make sure we don't get some random, list index out of bounds error or something like that if we pass in an empty list. We don't. Test cases pass that. And then finally, we will just generate a completely random list. All right, using the random module. I imported that all the way at the top here, import random. No, I need 2 lines there. And let's just see what that does here for a test case. All right, so this line down here, the random sample created this completely random array. 51, 80, 14, 67, blah, 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 blah. Let's look at the result. I get 3, 4, 14, 26, 27, 35, 36, 40, 41, 45, 46, 51, 67, 71, 73, 74, 78, 80, 95, 98. Everything in here looks like it's in order. I don't see anything that's out of order there. So that would be your selection sort. Pretty simple to understand, pretty simple to implement, not super efficient. Remember O to the n squared time complexity for both best, average, and worst case. But since it's so simple, if I was only sorting like some very small size lists or arrays, I might consider it. But anyways, that's selection sort. So if you like the video at all, again, just like, subscribe. Send me a comment about what you liked about it. If you didn't like it, that's cool. Just go ahead and send me a comment about what you didn't like and what you want me to change. So look for videos here in the near future about the rest of the kind of sorting algorithms out there. All right, thanks for watching.